In this video we're going to look at transmission correction and how it relates to measurements from survey spectra and high resolution data. I've got an example of a material that contains lithium, which is a very low intensity peak. The cross section with aluminium anode X-rays is about 18 times lower than the cross section for carbon. So we would have to collect for a long time to get the same signal to noise for lithium as we would for carbon. I've also got within this spectrum a carbon peak that has some sort of chemical state. I'm not quite sure what it is, but it's certainly there, and if I look at the carbon measured at a high resolution mode, so this is Parsons 20, I can identify various features within the data that require a peak model. I would not be able to do that from the survey spectrum, which is at Parsons 160. So the resolution in terms of energy is not sufficient to construct a peak model and look at the structure that is in this carbon 1s. However, because of transmission correction, there's a method for adjusting the intensities so that we can compare signal from these two different operating modes, Parsons 160 to Parsons 20. If we didn't have this facility, then in order to do quantification of data such as these, we would have to measure narrow scan spectra with the same resolution that we need for the carbon 1s. This would be untenable if we are looking at lithium. It will take a long time to measure the lithium, and actually you don't have time necessarily with XPS because samples change the longer you measure. So it's not always an option to carry on measuring to get the signal to noise that you want. What we see here is the survey measurement and also the carbon 1s measurement. This was performed at Parsons 20, this was performed at Parsons 160, but they've been combined together using quantification. And this quantification table has come from the quantification option on the annotation dialog window. So this now has been constructed so that I can see the atomic concentration calculated from both the C1s and the survey. So the oxygen, fluorine, silicon and lithium, these are all being measured from the survey data, whereas the carbon is being measured from the high resolution data. These three windows you see here are all windows into the same data file. They are labeled 1, 2 and 3. So these are all the same data, it's just a different view into the same data file. And the reason I say that is because I want to show you that I've prepared one of these survey spectra to be a copy of the other. I've quantified the sample in terms of elemental composition using the survey measurement. So I've got the fluorine, oxygen, carbon, silicon and lithium all from the survey measurement, and these are the proportions that are being offered by the survey measurement at Parsons 160. When I come over here, I've got the same survey spectrum, but this time I've omitted the carbon 1s, and so I've only got signal from the survey measurement for these four elements, and the results for these four elements, as you can see, are identical, but the difference is now the carbon is being split into chemical state using the peak model. So these are results all coming from the Parsons 20 spectrum, and therefore we don't have to measure lithium using Parsons 20, we don't have to measure oxygen or fluorine with Parsons 20. We simply need the extra sensitivity that we get from Parsons 160 and the extra resolution from the Parsons 20 to construct a quantification table that gives us the information that would otherwise be missing if we just had the low resolution data. Most spectra come with the transmission function already included in the data file. It's not always the case, and sometimes one might like to update the transmission function. Perhaps it's a little out of date. So in this case, these data have been corrected by calculating a transmission correction based on a set of gold spectra. These are the gold spectra. They were survey measurements measured at different pass energies, and a selection of pass energies have been used to calculate a transmission curve, which you can see here. And this transmission curve is used to then calculate the transmission functions for the different pass energies which are applied to the data. Now, details about how this is all done is available in other videos, so I won't go into it here, but the importance of these calculations when we want accurate and precise quantification by XPS can't be overestimated.